Hello, everybody. I hope you're all doing well. We're going to be looking at a very brief introduction to static friction, and then I'm going to follow this up with a very short problem as well. Okay, so we'll look at static friction. All right. And when you look at the idea of static friction, there are many different theories of friction. Okay, the most common theory is the Coulombs law of friction, which is what we are going to be appropriating for our particular methodology. Okay, so many different theories. Friction that are available, and most or probably a majority of these theories are experiments or observations, okay, or empirical. Okay, so majority, I just want to write this properly. Majority of these theories are empirical meaning they're based on observations or experiments. Okay, and the most common among them is the Coulombs law of friction is the simplest of the case. Okay, Coulombs law, so we shall look at Coulombs law of friction. Okay, this is the simplest of the lot. All right. So Coulomb's law of friction, I'm just going to state down a couple of things that will be useful for us before we start looking at making use of this in a problem. Okay, Coulomb's law, these are based on empirical observations. This is also called as a Coulomb-Amontons law of friction, based on the French scientist Amontons. Okay, so this is also called the Coulomb-Amontons law of friction. Okay, all right, so Coulomb's law. Here are the basic facts. Okay, these are based on experimental observations. So first thing is that, well, I guess come back to my regular color. Okay, so first thing is that friction is a dissipative force. Friction is a dissipative force. That is, whenever you have a force of friction, it acts to slow down a body. Okay, that is the meaning of a dissipative force. Okay, then I come to the next point. So the force of friction always acts opposite to the direction of relative motion. Okay, so force of friction always acts opposite to the direction of relative motion at the contact surface. Okay, between two bodies. And all of this will become much more clear, once we start looking at some problems and so on. Okay, and the third thing is at that particular contact surface, the force of friction is tangent to the contact surface. Okay, so the force of friction okay, this is tangent to the contact surface of the bodies. Okay, and acts in a direction that resists relative motion. Okay, and acts to resist relative motion between the two bodies. That's a force of friction between two bodies, if you want to say. Okay, so force of friction between two bodies in contact. Okay, this is first of all tangent to the contact surface and acts to resist the relative motion between the two bodies. Okay, so these are the things. Now we come to the actual Coulombs law. Okay, there is a maximum or a limiting value of the friction force. Okay, this is called as a static friction force, and this is related by means of experiments to the normal force at the contact via the coefficient of static friction. Okay, so there is a limiting value. So there is a maximum or limiting value of the friction force okay, this is called as the maximum static friction force. Okay, and typically we will be labeling this as F mu max. Okay, so I'm just going to copy that, and I'm going to be calling that as F mu max. Mu is the symbol for the coefficient of friction, so F mu max. And from experiments we can say that based on observations, okay, we have the following relationship: F mu max is equal to mu s times n, okay, where mu s is called as a coefficient of static friction, or the static friction coefficient, different ways of saying the same thing. And then n is called as a normal force. N is the normal force at the contact surface. Okay, so now we come to certain important conclusions. Okay, so here is the following. So here are our conclusions for applying friction. Okay, so some conclusions. Okay, these are the conclusions or the summary of Coulombs law. Okay, first of all, F mu max is mu s times n, and this acts in a direction that resists relative motion. Okay, friction acts to resist relative motion tangential to the surface and so on. So that's all there. Now let's say F mu is the force of friction on a body. On body at the contact surface. Okay, then we have the following. If the force F mu that you obtain from calculation, okay, this is typically obtained by calculation, okay, if F mu is less than F mu max, then this implies that the body is in static equilibrium. This implies body in static equilibrium. Okay, this is the first conclusion. Second conclusion, if F mu is equal to F mu max, what happens? Then we say that the body is in static equilibrium, but motion is impending at the contact point, such that the body is about to move. Okay, so body still in static equilibrium, but motion is impending. Okay, when I say motion is impending, it means that motion is about to start. Okay. Implies that motion about to start. Okay, and then I come to the third situation where if I figure out that F mu is greater than F mu max, then I'm in a whole world of pain because this violates Coulombs law. Okay, so this is a violation of Coulombs law. Okay, so what does that mean? This means that the body is no longer in static equilibrium. Okay, which means that body no longer in static equilibrium, which means the body is moving, which means that the magnitude of the friction force actually will drop down due to motion. Okay, so F mu is now going to be mu k times n, where mu k is the kinetic friction coefficient. Okay, and typically mu k is less than mu s. So this is just purely to ensure that the Coulomb law is not violated. So you drop down to a mu k value. Okay, this typically happens when you do problems in dynamics. Okay, so these are the three conclusions. So, I guess if you want a very short, much briefer summary, so briefly. Okay, I'm going to have the following. F mu less than F mu max. Okay, or this means that static equilibrium. Then F mu is equal to F mu max is impending motion, but still in static equilibrium. And the last case, F mu greater than F mu max, this is dynamics, violates law of Coulomb. Okay, so in this particular case, F mu then becomes equal to mu k times n, where mu k is less than mu s, so that the law of Coulomb is still not violated. Okay, so this is like the very brief summary of what I have just written up there. Okay, so the things that we are interested in statics is that, okay, the situation of either static equilibrium or a situation of impending motion. Okay, so that's our interest here, and I'm going to explore this by means of a problem here. Okay, so let's look at a problem quickly. Okay, what is the problem? Very simple problem actually. I have a block on a surface. Okay, so here is the block. Okay, so block B, let's say. And this is sitting on fixed ground. Okay, so the other surface is not in any kind of motion. Okay, that's a fixed surface, and then there is an applied force on this block. Okay, so I'm applying a force on this block here. Let me call that force as capital P. Okay, let's say the mass of this block is given to me is 100 kilograms. Okay, and then acceleration due to gravity. Gravity G is 9.8 meters per second square, which I need to calculate the weight of the block. Then I'm told that the coefficient of static friction between the block and the ground, and the coefficient of kinetic friction, both of them are given to me. This is 0.1, this is 0.2. Okay, so coefficient of static friction between the block and the ground is mu s, which is 0.2. Okay, and then I'm just going to grab this so that I just copy that and paste that down here, and just remove some of these things, cut that off as well. Coefficient of kinetic friction is given to me as mu k, which is 0.1. Okay, and I'm asked to consider 3 cases of the force applied. So consider three cases for force P. In case A, the force P applied is equal to 150 newtons. Case B, the force P applied is 196 newtons. Okay, and then in case C, the force applied is given to me as 210 newtons. Now for each case of P, excuse me, for each case of the force P, figure out if the block is in motion or at rest. Okay, and of course for each case of this force P, I also need to find the force of friction between the block and the ground. Okay, so quick problem once again. As you can see here, I have a block. This block is just sitting on the ground minding its own business. Okay, the coefficient of static friction and kinetic friction between the block and the ground is given to me as 0.2 and 0.1. These are experimentally determined values. Okay, they will be typically given to you at the beginning of a problem. There is a force P that is applied on this block which weighs 100 kilograms, and there are different values or a range of the magnitude of the force P considered here: 150, 196 and 210. For each of the cases of force P, is the block at rest or in motion? Okay, that is the first thing we got to figure out. Then for each case of the force P, based on what your conclusions are for the previous part, find the force of friction between the block and the ground. Okay, so this is what we need to do. Here is my strategy. Okay, so strategy. This is what I do for all the problems in friction. Okay, I'm going to assume the block to be in static equilibrium, and then I start exploring each and every case of the force applied. Okay, so assume the block to be in static equilibrium. Okay, then I will go through the different cases of Coulombs law. Okay, and then for each value of P, obtain the friction force between the block and the ground, and see if it satisfies or violates Coulombs law. Okay, so this is my typical strategy, and the main thing is I assume the block to be in static equilibrium to begin with. Okay, so if the block is in static equilibrium, then I have to draw the free body diagram of the block. Okay, so that's essentially what I'm going to be doing. I'm going to be grabbing that block from here. Okay, so here is the block. So I'm going to copy that and I'm going to draw its free body diagram. Okay, so free body diagram of the block. Alright, so I'm going to copy that and paste that down here. Alright, so here is the block with the free body diagram, which will be drawn in a second. What are the forces acting? The forces acting are, I'm going to have the weight of the block which is acting vertically down, right? So this is the weight, which is mass times acceleration due to gravity. Okay, so this is going to be 100 times 9.8, which is 980 newtons. Then what else do I have? I have the force of friction and I have the normal force. Okay, so the normal force at the contact surface is going to be acting in this direction. What about the force of friction? The direction of force F mu is opposite to the direction of probable motion. So the block is pulled to the right, so the probable motion is going to be to the left. So I'm going to have F mu acting this way. Okay, I just want to make a very brief note. Direction of F mu is opposite to the direction of probable motion at the contact surface. Okay, so that's what I have assumed here. Alright, there are no dimensions given for the block, which means that we don't need to use any moment balance, which means all we have to do is just use only the force balance. Okay, so note that there are no dimensions given. Which means that we cannot use any moment balance equations. Okay, or moment equilibrium equations, but we will make use of it at later problems when we are given the dimensions and so on. Okay. Alright, now for each case of the problem, the free body diagram is the same because this is just a generic free body diagram. Okay, I just want to make a brief note of it. So for each case of force P, the free body diagram is the same. Okay, which means the equations will also be the same. I just have to apply them and see. Okay, so that's typically what I'm going to be doing. So I start off with the equations. Okay, since this is assumed to be in static equilibrium, forces in the x direction is 0. What are the forces acting? I have the force P minus F mu is equal to 0, which means that force P is equal to F mu. Then I say, hey, sum of all the forces in the y direction is 0. What are the forces in the y direction? I have the normal force minus mg is equal to 0, which means the normal force is equal to mg, which is 980 newtons. Okay, so then we are good to go. And we also have Coulombs law, right? One more equation that we can use. Coulombs law says that I have a maximum force of friction F mu max, which is equal to mu s times n, which is 0.2 times 980. Okay, so this is equal to 196 newtons. Okay, so which means that F mu max is equal to 196 newtons. So here are the things that I have so far. Okay, and F mu max is equal to 196 newtons. Then I start looking at each and every one of the cases. Okay, so case A. The force applied is given to me as what was that, around 100 newtons, I think. Okay, 150 newtons. So P was 150 newtons. But we know P is equal to F mu, which means that F mu is 150 newtons. And we then do the comparison Okay, so compare F mu with F mu max. Okay, F mu max is 196, 150 newtons. F mu max is 196 newtons, which means that F mu is less than F mu max, which means that this is in static equilibrium. Okay, body is in static equilibrium. Which means the body is not moving anywhere. Okay, so which means for case A, F mu is equal to 150 newtons and the body is in static equilibrium. Alright, so that's the end of case A. Then case B. In case B, we are told that the force P applied is 196 newtons. Okay, but we know P is equal to F mu, which means that F mu is equal to 196 newtons. But we also know F mu max is 196 newtons from where? From here. Okay, so I do the comparison. When I do the comparison, F mu is equal to F mu max. Okay, that is the important thing. In every one of these cases, I compare F mu with F mu max. Okay, here also I do the comparison. F mu is now equal to F mu max. Okay, which means that the body is in a state of impending motion. Okay, so this implies that the body is still in static equilibrium. But is on the verge of moving. That is impending motion. Okay, so which means that for case B, F mu is equal to 196 newtons. This is the friction force on the body. Okay, that is important. So something I just want to mention here, this is the friction force on the body. This is not the maximum friction force or anything. This is the force on the body. Okay, so F mu is 196 and body is in impending motion. Okay, then I come to the last case. The same idea. Okay, nothing different here. Case C is what I think I call it. Okay, if I look at case C, what is the situation for me? Essentially, I know that P given to me is around 210 newtons. We know that P is equal to the force F mu based upon the idea of static equilibrium at the initial part of the problem, which means that F mu is equal to 210 newtons. We also know F mu max is 196 newtons, right? And if I do the comparison, F mu max is actually less than F mu, or F mu is greater than F mu max. This is a violation. This violates Coulombs law. Okay, which means that our assumption of static equilibrium is wrong. Okay, so this implies that body is not in static equilibrium. body in motion. Okay, as you can see. Okay, and in this particular case, so for case C, what should be the friction force? The friction force cannot be larger than the maximum force of friction. So the friction force has to be reduced to mu k times n, which is 0.1 times 980, which is 98 newtons. Okay, so F mu is equal to 98 newtons and body in motion, which means you need to handle it using the tools of dynamics, and that's something that you learn in the next semester. Okay, so these are the different cases that we have exercised essentially in this particular problem. Okay, so very brief recap of this entire lecture. In a sense, this is a short lecture, as I told you. Okay, static friction, many theories of friction, many of them are experimental or empirical theories. Most common among them is Coulombs theory of friction, which is also the easiest of the lot, really. So which is why we are using it. But it's very useful because it gives us a very good idea of what's happening on the scale of friction. Okay, Coulombs law says that the force of friction is a dissipative force, which means that it tries to work against the tendency of bodies to move. Okay, the force of friction is always acting opposite to the direction of relative motion at the contact surface, and it's tangent to the contact surface, as you have seen in the problem we solved, and it acts to resist the relative motion. And the key thing is there is a maximum or limiting value of the friction force beyond which the friction force on a body cannot be larger as the maximum static friction force, F mu max. And these are based on observations. F mu max is mu s times n, which is mu s is the coefficient of static friction. Okay, and then some useful conclusions can be drawn. F mu max is mu s times n, we know that. So if F mu is the force of friction on a body, if the force of friction is less than the maximum friction force, body is in static equilibrium. If the force of friction is equal to the maximum friction force, the body is still in static equilibrium, but the motion is about to occur. Okay, which means that it is impending. And lastly, if the force of friction is greater than the static friction force, this violates Coulombs law, which means that this cannot be possible. So the force of friction actually has to reduce down to a smaller value, and the body is no longer in static equilibrium, it is actually in motion. You're doing a problem in dynamics now. Okay, so these are the three situations that we have studied, and we exercise that for a problem. Here is a block sitting there minding its own business. There is a force P that is applied. Force P tries to pull the block. What's going to happen? Depends on what the magnitude of the force P is. Okay, so how do I start this problem? Assume it to be in equilibrium. Obtain the equations for equilibrium. Forces in the x direction is 0, forces in the y direction is 0. I don't use the sum of moments here because I don't have any dimensions given to me. So what am I going to do? So hopefully I don't need the sum of moments. I sum forces in x and y direction. I get the forces in this manner. P is equal to F mu, and the normal force is 980 newtons. Maximum force of friction is obtained from Coulombs law, which is 196 newtons. In the first case, the force P is 150, which is the same as the friction force. So 150 is less than 196, so the body is in static equilibrium. Okay, that's the first conclusion that we have. Second case, force P is 196 newtons, which is the same as the friction force on a body. If I do the comparison between F mu and F mu max, I see that they're equal to each other. So the body is still in static equilibrium, but it's on the verge of moving. So motion is impending. So it's about to move. Even a very small, gentle breeze is going to start making it move. Okay. Last case is where I have the force of applied force is 210 newtons, which is by force balance or static equilibrium equal to the force of friction. If I then do the comparison of that with the maximum friction force, I see that this violates Coulombs law because the force of friction cannot be larger than the maximum friction force. So the body is actually not in static equilibrium, the body is moving. And since the body is moving, the force of friction has to reduce down to a value less than the maximum static friction force. So I get that by multiplying it by mu k, which is 0.1 times 980 normal force, which is 98 newtons. So now the force of friction is less than F mu max, but the body is moving. That is important. This is not static equilibrium anymore. All right. I hope this was a fun lecture. Take care of yourselves and stay safe. And we're going to solve more problems on friction in the future. All right. Thank you very much. Bye bye.